So life on Earth, all of it, has certain characteristics, right? Like 8 things that we know is true of every living thing, including they have cells. But of course, the cells are different, which is the basis of the first 3. The top 3 categories, the biggest categories we divide life on Earth into is the. So we used to just say it's bacteria and then not bacteria. But then we found these guys, the archaeans, which are bacteria that are so freaking different than regular bacteria. They're more different genetically from normal bacteria, like the kind that gives you strep throat. They're more different genetically from those bacteria than either of them, or than the new bacteria is from us. Is that right? Something like that. They're really, really different from each other. So they get their own 2 huge categories. Okay? And then everything else, including fungi, plants, protists, and animals, they get their category. So let's put that into a chart that's easier to grasp. It's less of a big mess of a tree. 3 domains, that's what we call them, the 3 big groups. This happened really only when we got good enough at reading DNA to realize that they're that different. I think the right way to put it, now that I remember, is the 2 domains of bacteria are as different from each other as either of them is from us. So this is the domain level is 1 tick above kingdoms. We used to just have 6 kingdoms. Now we have those 3 domains. Why is everybody flipping through their notes? Do you feel like you already have this?
No.
No, I was just seeing if I know the name.
Cool. I just always feel like I did something, and everybody's like, "What's going on?" So 3 domains, 6 kingdoms. Here's how it shakes out. Please do go ahead and draw this. So today, where are you going? I give you guys something on paper yesterday.
Oh, I
Today we're going to go through the first 3 kingdoms. This is basically 1, 2, and 3 here are the ones that are 1 cell. We're going to go through the simplest life forms on Earth. But a simple creature. It really was kind of a big deal when they found these guys. Because basically what we know, and what you're going to learn soon when we talk about early Earth, is that if you build a time machine, like if you're that guy or girl, don't go back too far. Like, don't set your time machine for like early Earth. Because first of all, too far back and you'll fry your face off. You'll just, spontaneously combust. But second of all, conditions, even once things cool down a little bit, there's like cyanide in the air, like poison gas, like it's not for you. We don't, cells like ours don't evolve until like almost 1 billion years in. Yeah. So don't do that. Still a little jealous. So basically, the life that does evolve when things are that crazy is evolved to fit that environment. And when Earth's environment changes to be less crazy and more amenable to us, the cells that evolved in the crazy environment have to find places on Earth that are still crazy, if that makes sense. And that's these guys. That's archaea. Archaebacteria. Archae literally means old, right? Archaeology is digging up old stuff. So archaebacteria are the old bacteria. They are the oldest organisms on Earth. And by that, I don't mean that the bacteria themselves are years old or a billion years old, but that their ancestors were the first cells on Earth, at least that we know of. We have found fossilized mats of bacteria, because they do live together in these mats called stromatolites. We found fossilized stromatolites of them dated approximately 3.7 billion years old. That's on an Earth that's itself only 4.5 billion years old. So they were there earlier than any other cell we know of. They are unicellular. Sometimes they hang out together in colonies. Otherwise, we never would have found fossils of them. They are prokaryotes, of course, because they're bacteria, right? It means they don't have a nucleus, they don't have membrane-bound organelles. Like all the other prokaryotes, they do have cell walls, so their cell walls are made of different stuff. Bless you. We often call a lot of these bacteria extremophiles, and that's because they live in environments that we consider extreme. Extremely hot, extremely anoxic, that means no oxygen, extremely salty, some of them. Like, not like that. Angry bacteria. And the question why is answered by, well, because that's what the early Earth looked like. Because they've basically found places to live, the bottom of hot springs in Yellowstone, hydrothermal vents at the bottom of the ocean, spewing out toxic sulfur stuff, toxic to us, to them. That's what the early Earth looked like. Lots of volcanic activity, crazy poison gases everywhere. That's where they can still exist. It's places that look like the early Earth. So that's why. 3 categories include the methanogens. These are the ones that make swamp gas, methane, at the bottom of swamps. Halophiles. Nothing to do with the video game. Halo is a root that means salt. So these are the ones that like it really, really, really salty. They live in certain super duper saline seas and lakes. Do not take any lip. And big word meaning something very simple. You know how I feel about that. Extremothermophiles. This means they like it really hot. Some of them are autotrophic, meaning they can make their own food. Some of them do it the way you'd expect. Called photoautotrophs. They can do a primitive form of photosynthesis. But the ones that really made us kind of reevaluate and change our understanding of the early Earth are the ones that can do their own, that they can be autotrophic, they can make their own food without sunlight. They're called chemoautotrophs. I don't know why that did that. Chemoautotrophs do something called chemosynthesis, not to be confused with photosynthesis. I think we mentioned it in ecology. I told you I'd show you a video about them. This is that time. It's only a 3-minute video, but honestly, we found these guys in like 1977. We found these hydrothermal vents deep under the ocean off the coast of South America somewhere. and sent like old school submarine explorers down there to take video, and the video is pretty incredible, even from 1970. So I don't know if it's from 90, it's probably from the 80s. So I'm going to show that to you. Because the bacteria that do the chemosynthesis, you know how all life on Earth depends on plants? Yeah, not this life. They're the plants of their ecosystem. And so there's this whole food chain built on these chemosynthetic bacteria. Doesn't look anything like life we know. Sound. Oh, not that one. That one. This might work. It does work.
Business has completely changed.
Because, of course, the first cells on Earth wouldn't have plants to feed off, right? They wouldn't have a base to the food chain already there for them. So chemosynthesis is maybe a partial answer to what the first cells on Earth did for energy. We'll get more into that stuff as we get into the Earth's history. Whoops. Okay, come on. All right, good. So that's them. That is the archaebacteria. Then, of course, there's regular bacteria. We'll hit them next. So archaea, regular bacteria, and then the rest, right? Protists, plants, fungi, and animals. Here's regular bacteria. We actually call them eubacteria. Eu means true. It's a word root that means true. Some stuff in common with archaebacteria. They are mostly single-celled. Although, again, some of them like to live together in colonies. They are, of course, prokaryotes, meaning no nucleus, no membrane-bound organelles like you learned in chapter 7. And they also have cell walls, but their cell walls are chemically super different from any other cell walls, from archaean cell walls, from plant cell walls, and from fungal cell walls. And some of these are autotrophic, although they're all photosynthetic. Chemosynthesis only happens in the air. More coming about these bacteria when we get to our disease unit, which is coming soon. By the way, this is the last unit of state curriculum for the state test. So we're almost ready. We'll start doing practice tests and stuff like that soon. I promise I won't make it too painful. You guys are pretty much there. You just need a few kind of test-taking tip type things.
Can we open frogs?
No, we don't do frogs.
What do we do?
We typically do 7 different animals. Each group gets a different animal, and you teach your animal to the class. Not sure what we're allowed to do this year with like grouping protocols, but we'll do something.
That's like the one thing in high school thought, oh, I can't wait till I say.
Mm-hmm. And now you're in this class, and you're like, there's so much more to science.
Yeah.
I just love it so much. Thank you, Mr. Sam.
I was like, you just open my eyes. You can't tell that his ears. You hear sleep.
That's why I cry myself to sleep. Into our third domain. I'll just hit one kingdom here. You did it again. I gotta edit that out. You ever look at a drop of pond water under a microscope? Holy cow. Whole world, right? Like, oh my gosh, there's all these weird little alien-looking things. Most of those things, some of them are really primitive animals, but most of them are what we call protists. And they're the most primitive form of eukarya. Eukarya, again, being the ones with a true nucleus, membrane-bound organelles, and belonging to one of 4 kingdoms: the protists, the fungi, the plants, and the animals. We're just going to look at protists. Taxonomically, meaning according to like our classification science, protists are definitely the weakest. And I don't mean like the other kingdoms beat them up. I mean like they're in that kingdom just because we couldn't figure out where to put them, basically. They're the ones that don't fit anywhere else. They're the ones that were almost qualified to be animals, or almost complicated enough to be plants, or almost cool enough to be fungi, but not quite. So we put them in protists. They're basically the proto versions of each of the other three eukaryotes. In fact, that's how we classify it: the animal-like protists, the plant-like protists, and the fungus-like protists. If you've ever seen a slime mold, gross stuff that grows on rocks and other stuff, that's a fungus-like protist. So if you've ever seen like plankton, there's two kinds. There's the animal-like plankton and the plant-like plankton. Right? Zooplankton and phytoplankton. That's how we classify them. Are they almost like plants? Are they almost like animals? Are they almost like fungi? So some of that might even look familiar if you've looked at pond water. We'll have to get a little bit warmer, and we'll do that ourselves. Very diverse, just as diverse, almost as diverse as the other kingdoms. Some of them unicellular, some of them colonial like bacteria, but some of them even multicellular. There's, algae and seaweeds that qualify as multicellular. Not quite complicated enough to plants.
The seaweed is a plant.
Depends on the seaweed, but yeah, a lot of the seaweeds out there are protoplants, protists. Some of them can move. And if you're wondering why I say motile and not mobile, it's that mobile just means you can move it around, like it can be moved, whereas motile means it can move under its own power. And so there are plenty of protists with cilia or flagella. If you remember them, remember them? Remember my interpretive dance?
Yeah.
Cilia, flagella.
I think I've locked it out.
It is vivid. Some of them just kind of float around. Some of them heterotrophic, meaning they got to eat. Some of them autotrophic, meaning they don't. And as I mentioned, the way we classify them is what they almost qualify for: animal-like, plant-like, and fungus-like. And there you go, halfway through. All that's left: fungi, plants, and animals. And we're gonna and notice we're not doing a lot here as far as classification. We're just giving you the bare bones of what this group is about, how to recognize it as belonging to that kingdom. That's what we'll do with animals, plants, and fungi as well. Just their larger characteristics. We'll get deeper into animals, assuming we have time after our disease unit. Once we've taken the state test, we'll start to get into some animal classification. I want to give you one more practice with cladograms before I kind of drop you into the ocean of this computer simulation about cladograms. It's really going to get it in your brains. That's the game. We're going to do the paper first. Let's see how this goes. I haven't used this one before. Okay, so on the front, you've got, again, mostly just information. That cladogram on the front, you can see the animals, but the derived characters are not given to you. They're just lettered. And so you got to kind of figure out which ones you think those derived characters are. So you put a letter next to each derived character to match it up. Then create your own. And so it gives you 5 animals. And you got to figure out how the derived characters shake out. And so you put, I think, basically just a check mark, right? That looks like what you would do. And then you draw the cladogram yourself. See how it goes? I think it's about the same level of difficulty as yesterday's. Opposable thumbs are thumbs you can do this with, which a lot of the apes and stuff don't have. They can't. It's a muscle that's here that lets you do that. Grasping.
Tigers probably don't have that muscle, do
Correct.
they?